This would be a series on differential forms, and we'll begin our introduction to the course by discussing what are called the tangent spaces. So we'll start by our first definition of the course. We'll define our tangent spaces by supposing that you have a curve C that belongs to a real dimensional space or real number space of 2 dimensions. And then suppose that you have a point P that is on this curve. So it's represented like this. Now, having said this, the tangent space then, which will denote it by a T, the tangent space is tangent at point P to the curve C. It is a set of all vectors Vi that are tangent to the curve C at P. Now, let's sketch what I have just written. So this is my axis, and on this, let's sketch a curve C. Suppose this is your curve C. Now, on this curve, we'll pick a point and draw a tangent to that point. So it looks something like this. This is your point P, and this is your tangent to that point P. This tangent is really a tangent space defined at point P. What makes it a space is that it's constructed by a span of all vectors Vi, right? And all of these vectors Vi are tangent to this point P, and it's made up of all of these small vectors. So you can do something like that. So these are all your Vi. Now what we'll do is we'll look at this picture of tangent spaces using our understanding of calculus 1. So let's move down. So we'll be using our understanding of calculus 1, and we know that we can define a function y equals f of x, right? And having this function, we can plot it. Again, I'll plot a curve. So suppose this is your curve y equals f of x. Now on this curve, we'll pick a point and draw a tangent space to that point. So this is our situation. Now this point P has x coordinate a, and corresponding to that y equals f of a. Now what we want to do is we want to find a vector v that is parallel to the tangent space TPC, right? Because the vectors that are parallel to this tangent space are the vectors that are constructing this tangent space TP of C. So how do we do that? Okay, so first we'll pick one point. We know how to do that, right? From calculus 1, we'll pick one point P, and let's say that this is my starting point. I'll pick another point on this tangent space. Suppose it's this one. And then what I'll do is I'll say that my vector is along this line. And how is this vector, let's call it V, how is this vector constructed? It's constructed by moving some part in X and some part in Y. Now this line, this one, we know what that is. We know that it is the slope of the graph. And how is the slope of the graph defined? It is f prime of a, the derivative of f of x at point A, x equals a. And this line, it's up to us. We can just parameterize it by unit. So we'll define it as 1. So it's just 1 units. Now, this is how you will calculate the vector between the 2 points. And now this vector v is equal to, now whenever we represent our vectors, we'll be using what I'll call the arrow brackets like this, 1. So this x coordinate is 1. What is y? It is f prime of a, f prime of a. So this is my vector v. Now we can think of this in our linear algebra sense. So in linear algebra, our tangent space Tp of C is basically just a span of all real multiples of vector v, or you can just say it's a span of all of your vectors v, right? So this vector v is just an arbitrary vector, and you can do this take a lot of these vectors v and put them on this tangent space, and that would be the span of all of these. So it's a span of your vector v, which is 1 comma f prime of a. This span is equal to, by using the definition of span, some number c and then f prime of a, such that this c is a number that belongs to the real space, right? This space R2. Okay, so now we have defined our tangent space as a span of all the vectors v, which are just all real number multiples of the vector v. So up until this point, there is a question that arises, and that is, we have a curve C and we have points on that curve, and then we have vectors that lie in the tangent space to that curve. So both of these things, the curve and this tangent space, they live inside a same ambient space, which is this one, R2, right? They're living inside the same ambient space. They're drawn on the same space. So how can we differentiate the points on both of these, right? So that's the question. So there will be points on this curve and there will be points on this tangent space. We want to separate them apart. And what we can do is, so the question I'll write is how to differentiate between points on curve C and tangent space Tp of C. That's the question. Again, the question arises simply because of the fact that both of these curves and tangent space, they live inside the same ambient space. So they share a common ambient space, which is R2. So what can we do about this? Well, one way to solve this problem is we'll use different coordinate systems for both of these things. So we'll use different coordinate systems for the curve C and tangent space Tp of C. So let's begin by defining our coordinate space on the curve C. Let's do that on the next page. So let's define first our coordinate system on the curve C. Okay, so we want to define our coordinates, right? So we'll define our coordinates x and y, and we'll represent them with these brackets on the curve C. So it's a function on curve C that goes to the real number space R2, right? Because we have these two dimensions, x and y, such that if I take x and y on the point P, what it gives me is x coordinate at point P and y coordinate at point P, right? So this is the definition of the coordinate system defined on the curve C. Now let's define our coordinate system on the tangent space Tp of C. This coordinate system, remember, the coordinate system on tangent space is made up of vectors, right? The tangent space itself is made up of vectors, so we are defining a coordinate system for our vectors, right? And what are those vectors on the tangent space? Remember, the tangent space Tp of C is represented, at least you can say that it is represented by the derivative dy by dx, right? It's the slope. The tangent space is the slope on that curve C. so it's represented by dy by dx. So you first, right off the bat, you notice that the coordinates x and y will be transformed to dx and dy, right? Dx and dy. But now it's the space is also made up of vectors, so we'll use differentiate between the coordinates and the on C and this one by these arrow brackets, and it will be dx comma dy. And this is defined on the tangent space TP of C that also goes to the real space of 2 dimensions, so that dx dy on the vector v is defined as the coordinate dx on vector v comma the coordinate dy again on vector v. So this is your coordinate system, right? And now let's define these variables x, y, and dx and dy. So x is a function, you can say, such that it's a number on C, right? It's a function of C that belongs to, or that goes to the real number of 1 dimension, right? Because it's just x coordinate, just one coordinate. And y is a coordinate on C that it belongs to, or that goes to, again, R1, 1 dimension. So these both combine together to make R2. Okay, next dx and dy. So dx is a function of the tangent space to C, and it is also in R1. Likewise, dy is a function of tangent space to C, again in R1. Alright, now let's use some of this and look at an example of a function that you're all familiar with, y equals x squared. So I'll first plot this function. We know that it will be a parabola or a parabolic function. So this is our graph. This is the function. This function is this is the curve C, which is just y is equal to x squared, right? Now what we'll do is we'll pick a point on this curve, right? Point P. So suppose that if I pick any point P, then I'll draw a tangent space to that point P, right? That was how we do it. So let's pick a point P and draw a tangent space to it. So this is what we have. This is the point P, right, on this curve, which has coordinates A, and then correspondingly, because y is equal to x squared, this y coordinate will be a squared, right? X squared, x is a, so a squared. Right, so we have this, and then we draw a tangent space to that point P, and this tangent space, remember, it is just a set of vectors V, right? Now again, we know that what we have to do is this vector is made up of these 2 directions. So if I can draw it like this one. This direction and this direction combined makes up this vector V. Again, the vertical direction, we know what that would be. That is just telling you the slope of this tangent. And the slope of this tangent is the slope of this curve at this point P. And we know the slope is just the derivative of y with respect to x. And that is, we know that it will be 2 times x, right? So this length will be 2 times x. And this length we'll just parameterize in unit. So it will be 1. Okay, so now we have this thing. We can define our coordinates. Let's say this is x and this is y, right? So x comma y, the coordinate system for our coordinates at point P is equal to, so what is x at point P, right? Let me write it like this first. X at point P comma y at point P, right? So let's see, what is x at point P? X at point P is on this x-axis, which is a, and then y at point P is on this y-axis, which is a squared. Now, for the coordinates on the tangent space TP of C, which is this vector V, at this vector V, so the tangent space will be defined by the coordinates look like dx comma dy, as we saw, and these arrow brackets. And these are defined on the vector V, so which will be again these type of brackets. So it will be dx at P, dy at P. And we can see that from this thing that dx at P is this 1, right? This is the dx. So it is 1. dy at P is this one. dy at point P is 2x. So 2x. All right. Now, instead of calling it x, we'll call it a, right? Because x at point P is just a, right? So we'll call it 2a. Okay, perfect. Now, we know that this one belongs to the xy belongs to the curve C, while this coordinate system is defined for the tangent space TP at C. Right. Now, from calculus, we know that this thing, dx dy, which is 1 comma 2a, you can write down your dy as 1 times this 2a, or 2a times the x part, which is 1, right? So what is that? That is just 2a. What was 1? 1 was dx, right? It is dx. So 2a times dx. And this defines your definition of the derivative dy by dx. If I take this dx over there, and I get 2a. So this is your derivative of the function f at a. Right. Now let's talk about the real space that we have, right? The real space R2. Okay, so what would this R2 be made up of? Let me write it down. So this is R2. How can I make R2? Okay, so if I take, it's a two-dimensional space. If I take two basis vectors, right? So one basis vector will be corresponding to the one dimension, and the second basis vector corresponds to the second dimension. And then I take those two, take a set of those two vectors, and then span those bases all over the space, right? That will give me this entire space R2, right? So what I'm doing is I'm taking basis vectors and I'm spanning them, right? So we'll take our basis vectors 1, 0. So these are bases, normalized, and I'll pick 0, 1, right? So this one is for one of the axes, so x-axis, and this one is for y-axis. So this controls the x-axis scale, and this controls the scale of the y-axis, right? And remember, this R2, it's a two-dimensional space, and then what we'll do is we'll span these bases all over, and we'll get R2, which just means that it is just the coordinates x, y, given that x and y both belong to the real space R, right? Individually, right? So x is one dimension, belongs to R1, y belongs to again R1, and they combine together to form R2. Okay, now what about the tangent space of R2, right? Of R2. So the tangent space to this entire space, real two-dimensional space, we'll call it TP at R2, right? What will that be? That will just be dx dy, right? And again, those dx and dy will be the basis vectors. But now, remember, this is the tangent space TP, so we'll use the arrow brackets because it's made up of vectors. And we'll pick bases as 1, 0 again, and 0, 1. Right? These are the bases. So we choose these bases so that this one scales the x-axis, dx axis, and this one scales the dy axis. Right? And then we'll span these all over. And what is that? That is just, again, in the same way, it is dx, dy, given that both dx and dy belongs to the real space R. Wonderful, right? So now let's see what does this mean, right? If we can draw a picture we'll understand what does it really mean, right? Now, if I want to represent my vector and the curve C, how will I do it, right? Suppose I want a tangent space 1, 2, right? Actually, let me write it in this way first. So we are looking for tangent space at C, right? Suppose the tangent space is at 1, 2. So we write it like this. It's a vector notation, again, arrow brackets on the curve on which lies on points 1 and 1. So let's plot what this would be on our axes. So suppose this is your axis. Let's bring this axis a bit to the left. Okay. Now let's pick our coordinates 1 and 2, which will be on the curve. So the coordinates 1 and 1, which will be on the curve. So that would just be a point, right? These coordinates are defined for the point P. So this represents the point P, right? And this represents the vector V, the coordinates for the vector V. So the coordinates for point P, suppose if this is 1 and this is 1, so it lies somewhere over here, right? This is the point P. Now on this point, okay, so again, note that we have our axis. This is our y-axis, this is our x-axis. Now on this point P, what will happen is you will be defining or putting another set of axes, dx and dy. How? So let's plot this vector now on this point 1, 1. This vector has coordinates dx as 1. So this is dx and this is dy. So dx is 1. So again we travel 1 unit to the right. So suppose this is 2, and then this is 2, and this is 3. But we're traveling now 2 units to the up. So 1 and then 2. So you come to this point. Now let's get rid of all of these. And let's draw our vector. This is the vector V, right? And what happened here is, again, how did we reach to this vector? We reach to it by this dx and by this, it's a vector, right? So we can move it to the left hand side, dy. It was over here, right? But we can just pick it and move it over here without changing its direction and without changing its magnitude. So we can do that. So this is dy and dx. Again, you can think of it as if you put another set of axes, dx and dy, at the point P that lies on the curve.